Hello everyone and welcome to another video. In this video we'll look at a very interesting topic and even more interesting results. So this is hiding in plain sight deep steganography. So first of all, what is steganography? Let's do a quick Google search here. So let me just open up this, or maybe it's visible. So let me just read this out. I have written this here. So by the way, this is Weights and Biases Reports, which is a great way to combine beautiful visualizations with text and code. So the link is in description. So if you're going to read or execute this along the video, I suggest you open that up in the description. So yeah, first of all, steganography is a technique of hiding secret data within an ordinary non-secret file or message in order to avoid detection. The secret data is then extracted at its destination. The use of steganography can be combined with encryption as an extra step for hiding or protecting data. So first of all, well, it's clear by the definition that it is a way of hiding something. So maybe you just hide a secret image or an image that contains a useful information inside some ordinary image, maybe something that is not a secret. Well, once it is hidden inside that cover image, the non-secret image is sometimes called cover image. You can send it across networks, put it on the internet, so that even if people can download it or somehow get their hands on that particular piece of data, they won't be able to see what's hidden until and unless you get to decode the hidden message. So this is what steganography is. So let me just show you an example of deep steganography. So this task of hiding and retrieving an image, when automated using deep learning, using end-to-end systems, is called deep steganography. So here's an example. So here's a cover image, an image that is not that important. So even if even if people take a look at it, no, it's not something secret. You don't want to hide it. And then the second column is the secret image. The secret image is something that you want to hide. So that has to be hidden. Now on the other half, the other two columns are the outputs. So the hidden image here is the output of a network that hides the image, that hides the secret image inside the cover image, to be precise. So if you can just, let me just zoom in a little bit. Okay, so let's see if I can further zoom. Yeah, so here you can see right here that the hidden image contains some traces of butterflies, right? This one. So this shows that it has done a pretty good job of hiding it, because you cannot make out that it's a butterfly. We can only do that now because we know that the secret image is a butterfly, right? So we can see some traces, but it has done a pretty good job. So this is the output of the encoder network that encodes it. And then finally, once the data is transferred, on the other side, you can have a decoder that will reveal the secret image. This hidden image will be input to the decoder network and it will reveal the secret. So this is how it's done. So let me just zoom out a little bit. Yeah. So this was one example, and the second example is the lady sitting on something. The lady sitting on dried grass is the cover image, which is not important, and I guess the fried chicken like dish or grilled chicken, whatever, that is the secret image. In the second or in the third column, it is hidden inside the cover image, and finally it is been revealed. So this is what we will build, a system that will automate this entire task. Exciting stuff. So let's proceed with the report, and if you have not opened it yet, just the link is in description. You can just walk along with me, right? So in this case, a full-size color image is hidden inside another image called cover image with minimal changes in the appearance, utilizing deep convolutional neural networks. So CNNs, yeah, of course, wherever there is image or a video, there are CNNs these days. So we will then combine a reveal network which will then reveal the secret image from the generated image. So here's a quick example. This is a secret image. It is hidden inside the cover image, this cover image, and the output is basically only the cover image. But of course, this image contains the data. This output image contains the data of the secret image, right? So here it is. Now, of course, this work is based on a research paper. This is based on the research paper that I came across. It's actually, this research paper came out in 2017, but I didn't even know that this field of deep learning existed. So I just discovered this recently, and I was intrigued by the applications, and it's really cool to be able to hide images and then get them back. Yeah. So in the above example, the first image is secret image, which has to be hidden. The second image is the cover image, which will be used to hide the secret image, and the third image is the result of hiding process, which is basically a redone cover image. Basically, it's a cover image which has been redone, right? It contains some of the data, like all of the data of the secret image. So here's a link to the research paper. It's called Hiding Images in Plain Sight, Deep Steganography, which is the same as the title of this report. So yeah. Okay, you can also reproduce these results, the results that I will discuss now, like these results, using this Colab notebook, which is linked here, and I have opened it here. So I'll just walk you through quickly, because it's a actually I have also cloned this repo. Okay, so this code is actually written in TensorFlow, and I guess it's deprecated TensorFlow code, because I have not written this code. I have just cloned the repository and added a few things to make it better, like just to be able to experiment with it, because this came along when I searched for the official implementation, and it's quite straightforward. So I thought that it didn't require reimplementation because everything worked. It's just a little bit deprecated, I guess. Like, it's not TensorFlow 2 code, it's I guess TensorFlow 1-ish code. So maybe there's that, but it's quite straightforward. So I'll just walk you through it. But here what I'm going to do is to be able to cover this research paper. It's really cool, so I really like it. Now, so first of all, let me just introduce you to the model, because if you get how this architecture is written, how this works, the code is just a piece of cake, right? So our goal is to automate the entire task of hiding as well as revealing the secret image or message. The architecture of the network is similar to autoencoder. So right, so the input goes into preparation network, like the first part, that is the prep network, right? That is S, secret image. Secret image goes into the preparation network. So S represents secret, C represents cover image, or basically an image that is not that important, that is not a secret, right? Okay, so it gets into the preparation network, and then finally the output of that prepared secret image will go into the hiding network along with the cover image, and the output is C dash, right? And that will be our generated cover image that contains the secret hidden message, but it's just not visible. So this performing this task, we will get one error term. So we want this generated cover image to be as similar as the original cover image as possible, right? That's why that is the only way we can measure how effectively the messages are hidden. So if the generated cover image is very similar, like it looks almost as same as the original cover image, that means that we have hidden it perfectly. So the first error term that we are trying to optimize is the absolute difference between the pixel values of the generated cover image and the original cover image. So if we optimize that, the first task, that is to hide the image, is done perfectly, right? The second task is to reveal in the reveal network, right? So what this network does is it will reveal the secret from the generated cover image, and that secret will be S dash. Now the error term 2, yeah, of course it's quite obvious that it should be the absolute pixel difference between the generated cover image and the original, the absolute difference of pixels between the original secret image and the generated secret image, right? So this is it. So our secret should also be as close as the original secret, because we cannot, it's a secret message, it's something important, we cannot tamper with that. So if we optimize these two terms together, we have an end-to-end model. So this is what this research paper talks about. So again, let me just quickly go through some of the underlying details of the network, and then we will get to the results and experimentation part. So the network consists of three parts: the preparation network, the hiding network, and the reveal network. Now we'll stack these three parts together to form an end-to-end system for hiding as well as revealing the image. That's obvious, right? So here's the tensor board visualization of that model. First part is preparation network, second part is the hide network, and the third part that has been maximized for you to visualize is the reveal network. So all of these three networks have similar architecture, if not the same architecture. So visualizing one of them is enough to understand what all of them do. So there are three layers of operations, right? And then finally and all of these operations are convolution operations. So finally we'll stack the outputs of all of these 3 convolution layers, and then we'll get a three channeled output, which will basically be an image. So this is what's happening here. And of course you can experiment with the size of filters. That has been done on the internet a lot. You can get different implementations. People say that 3 cross 3 convolutions work better sometimes 5 cross 5 convolution works better and of course it has also like a lot of experiments have already proven that odd filters work better than even filters. So of course people have tried that a lot. Again, let's see what these networks in theory what they do. So one thing that was not clear to me when I read the code online, because that's what I do. I always read code first and then the research paper, not always, sometimes. So yeah, it was not clear what preparation network did, so that became clear after reading the paper. So prep network prepares the secret image to be hidden. This component serves 2 purposes. First, in cases in which the secret image, let's say of size m cross m, is smaller than the cover image, the preparation network progressively increases the size of the secret image to the size of the cover image, hereby distributing the secret image's bits across the entire n cross n pixels. So it's really important. So let's just say you have a small larger cover image and a small secret image. The message will not be hidden across all pixels of the cover image, and we want that. We want to hide it across all of the pixels, because in that way we get more pixels to compute, right? We get more flexibility, so we want that. Another important purpose of the preparation network is to transform the color based pixels to more useful features for succinctly coding the image, such as edges. So what this does is it will convert the color based pixels, like the color based features, into some other features that can be encoded into edges or things that are not colorful, because if you hide something that is colorful in the background, that will obviously show up in the cover image. So we reduce the colors, we suppress the colors, and we save that data, basically encode that data into some of the things that can be easily hidden, such as edges and shapes and stuff. And finally, the reveal network knows how these things have been encoded from color pixels to shapes, so it can just do the inverse operation, and we get the colors back. And sorry for the noise outside, it's really noisy, I know, just don't mind it. Right, the second network is pretty simple. The hiding network takes the output of the preparation network cover image and creates a container image, basically an encoder. The rightmost network, reveal network, is used for the receiver image. By the receiver image, it is the decoder. It receives only the container image. So the second network gets both the images, right? The prepared input, the prepared secret image, as well as the cover image. Loss function, we have already gone over it. I guess the only modification here is this term called beta, which basically is the level to which you want to preserve the secret image. So I keep it to 1, and most of the implementations keep it to 1. You can just experiment with it. So it is a really experimental thing, this paper, but just by changing one hyperparameter, you get so many different results that this is what actually intrigued me. This is what actually excited me in the first place to experiment with this. So now let's see what dataset we are going to be training this image on. So yeah, we will train this on our own. So tiny ImageNet dataset. So tiny ImageNet dataset is basically a dataset consists of 2000 images of dimension 64 cross 64 cross 3. So to train a deep steganography model, we don't need classes and things, right? We just need pairs of images. So it's very simple to create our own data. What we'll do is we'll take tiny ImageNet dataset, and then we'll make pairs of cover image and secret image from the dataset. So finally we have 1000 pairs of cover and secret images. So this is the simple code for doing that. Now finally, optimization. We'll now optimize our model with different combination of various hyperparameters. So as I said, just by changing a simple hyperparameter, you'll get drastically different results. Just bear with me, for in a minute I'll show you these different results. The task of choosing the best run according to your needs can be easily automated using weights and biases sweep. That is why I'm using this weights and biases reports, because all those streams can easily be imported, right? And I'll go over that in a minute. The task of choosing the best, well, of course, along with beautiful visualizations, right? So I have experimented with learning rates, activation functions, and the number of epochs. The following parallel coordinates chart shows how these affect the mean reconstruction loss. Mean reconstruction loss is basically how different the reconstructed image is from the original image, right? So I have experimented with these parameters: learning rate, activation function, epochs, and mean reconstruction loss. So this, and I have imported this beautiful visualization from weights and biases. So I have used 2 learning rates, 2 activation functions, 2 values for epochs, and the best performing model was with learning rate this particular 1e minus 3, and the activation function ReLU, and epochs I guess 300, and the loss was somewhere around this value. So this is how this visualization is really useful. We were able to identify the best run among, I guess, 6 or 7 runs so quickly. So we'll see if our deduction from this visualization is consistent or not in a minute. We'll actually inspect the outputs. The major takeaway from this chart is that keeping other hyperparameters or other parameters same, ReLU activation function optimizes significantly faster than tanh. Let's just see if we keep everything same, such as epochs and learning rate, right? Still, the ReLU activation function, the model with ReLU activation function, does optimize much faster. So, for example, here we have learning rate. Let's just consider this learning rate here, and ReLU, and again, it is, I guess, the second best value. And then, if we just look at tanh, right, it is, I guess, it is quite, yeah, it's visible that the value of the loss is higher in this case, and the same happens with this learning rate as well. So you can just check it out on your own. The link is in the description. Yeah. Anyway, we also get these visualization: batch reconstruction loss and mean reconstruction loss, activation function, learning rate, and number of epochs. So as you can see, at higher learning rate, the models with tanh activation functions don't learn anything. These are just flat curves. Again, this happens here as well in batch reconstruction loss. So again, metrics show that tanh models with tanh don't optimize that good, right? These are again some visualizations that can help you deduce which parameters are most important. But now let's look at the outputs, right? So first, let's compare the output of top 2 models. The top 2 models are the 2 models with the least reconstruction loss. So the outputs are as follows. Let me just maximize this so you can see. Okay. So here's the cover image. The first column is the cover image. The second column is the secret image. The third column is the encoded cover. The fourth column is the decoded secret, and the fifth and sixth columns are difference between the encoded cover and the original cover, and the difference between the encoded or decoded secret and the original secret. So that's why they are black. So if we are very close to the original image, then these both rows are going to be black. So this shows that these models perform really well, because these are like totally black. You subtract pixels from pixel, and if both the pixels have almost same value, you will get value that is very close to 0. That means 0. That means black color, right? So you can also see that the secret images are hidden perfectly behind the cover image. So the secret image right here is not visible. Only the bridge is visible, and it is same for all of these things. Again, this model also works pretty well, but one factor that can prove that this first model is better than the second model is that if you look at the difference of cover images, this particular column, you'll see some data is left out here. It is not totally black, which means there was some difference between the cover image and the encoded cover image. So yeah, that's the takeaway from this beautiful visualization. Now well, I've just explained what these things, what these rows were. Now let's study the effect of activation functions. This is what this report is all about. So as you can see, and also I have already discussed that the tanh activation function doesn't optimize well at higher learning rates. So let us now study the effect of activation functions on the performance of the model. Below we have side-by-side comparison of two models with all the same hyperparameters that only differ in their activation functions. One uses ReLU and one uses tanh. Let's see. So, well, the first model, we have already looked at it, it's the best performing model. So let's just quickly look at the second one. So if you will see in the second model, of course it also hides the images quite well, not as good as the first model, and which is quite evident by this diff cover and diff secret columns. There is some data present here. But another takeaway would be that the cover image, although the secret is hidden in the cover image, the colors of the cover and embedded encoded cover image changes a lot. So in the first one, as you can see, yellow becomes orange, and of course in this second row you can see yellow becomes orange or brownish. The third one does a pretty good job again, and this one is quite evident. I guess this greenish blue has become dark blue or navy blue, and yeah, all of these things, there are some inconsistencies. So this proves our hypothesis that ReLU actually performs better, not by a huge margin, but it does. But another important takeaway is that ReLU also performs good at higher learning rates, and tanh activation just breaks completely. So yeah, now let's look at the effect of learning rate. That's what I talked about, right? So let's see. At higher learning rates, it just doesn't learn anything. tanh activation model doesn't learn anything. As you can see, diff secret almost retains everything from its secret image, right? So encoded and decoded images are basically just noise, nothing else. But at a lower learning rate, it performs pretty well. These are both tanh activation models, right? So again, this is ReLU, and ReLU performs good on both high activation, and in fact it performs better at higher activation than at lower activation. So I guess ReLU is more stable for the hiding and the retrieving part of deep steganography, right? So that is it. Now I'll just quickly walk you through the code. It's quite straightforward. So you install weights and biases, download the dataset, unzip that, import a bunch of things, and then it's basically loading, and then divide a dataset into pairs of 2 right here, then show the dataset like just example, and here is the reveal loss. Full loss will combine the reveal loss as well as the hiding loss. Now here is the network part, right? There's a preparation network. Up until here there's preparation network, there is hiding network. These are just simple encoder implementations, right? And this finally is the decoder network, just repeated convolution layers, nothing else. So as you guessed that this is not some beginner level thing, like I'm not explaining how convolutional neural networks work, so I expect that you know that. It is just one of these really cool applications of deep learning that I came across and I wasn't aware, so I just thought I should share this. So yeah, it's not something that is beginner friendly. I should have said that in the beginning, but anyway. So yeah, here it is. It will just return the decoder network with some minor bug fixes. And finally, here's the full model. Here we'll combine we get the input, secret input, and input cover. So we'll make an encoder by using call encoder, make encoder method. We get the encoder here. We make the decoder here. We'll set the optimizer, and then there is the C prime, which is basically the output of the encoder, and then the S prime is the output of the decoder. And finally we'll just put them all together to create the model in loss, and here we will return encoder, decoder, and autoencoder. Autoencoder just combines everything together. right? If you want to use learning rate scheduler, you can use that. I have not used scheduler, but if you want, you can just use this manual scheduler that it's provided. I'll also link the original repo in the description, from which I have forked and edited a little bit. So here is how I have performed that experiments using weights and biases. So I have initialized a project called Steganography, and then I have selected a method random to randomly choose hyperparameters. And here you pass in all the parameters that you want to experiment with. So learning rate can be different values like 0.005 is just an example. I have just set it up right here, and then activation can be ReLU as well as TANH, all of these things. So it's just that. So I set up an example right here for if you want to experiment with this, right? So you can just change it. So by default, it just contains one value. And then finally here is the train part right here. Just put everything together, the normal training loop. I won't go over that. It uses TQDM to track the progress and all of that. And that is it. Finally, I've just logged the output to weights and biases so that we can view them like this in this form that we have. So there's that. And also I have logged where is it, somewhere here, I guess. Yeah, I have logged here mean loss. That is it. So that's why we have got like two graphs, this graph of loss and then this output. So here is the entire experimentation with deep steganography and its application. So I'm really excited about this field of deep learning and to see what this does in the future, like what are the things that we can achieve with the real world applications. Of course, so many businesses will utilize this to build so many new functionalities. So this was a quick, I guess, one video thing. And also I'm working a little bit with NLP these days, and I think that I will do a series on Hugging Face NLP or something related to that, because Hugging Face is released I guess version 0.3, and that is really great. So I think I will do a full walkthrough of everything Hugging Face can do, all the functionalities it provides, or maybe not just Hugging Face but so many other things related to deep NLP. I'm looking into that a lot these days, so just to let you know, I am planning on doing a lot of things, just running behind a schedule level. So thanks for watching, and I will see you in the next one.